The third polytropic process is the constant temperature process. A non-flow isothermal process can be visualized by a perfectly cooled piston cylinder arrangement containing gas inside. To start our analysis, let's again assume that heat is going to be transferred into the system. This will cause the gas to expand from point 1 to point 2. The isothermal expansion process can be represented in the PV diagram by a curve that is sloping downwards to the right from point 1 to point 2. This is the shape of the graph because remember from Boyle's law that volume is indirectly proportional to pressure. This means that the higher the volume of the gas, the lower is its corresponding pressure. The direction of the graph in the TS diagram is like that in the PV diagram. However, since temperature remains constant, the isothermal heat addition process will be represented by a horizontal line going from the left at point 1 to the right at point 2. We can also visualize the shape of the PV and TS diagrams for a constant temperature heat rejection process. In this case, gas will be compressed inside the cylinder, causing the positions of states 1 and 2 to interchange in both diagrams. The PVT relationship for isothermal processes can be expressed using the equation of state. In its other form, remember that we can simply cancel out T1 and T2. So besides the equation of state, we can express the PVT relationship in isothermal processes as V2 over V1 equals P1 over P2. Now these are the alternative forms of the equation for the non-flow work. I will be deriving these forms in the next slide. Remember that the variable of integration in this integral is volume, so we need to express the pressure in terms of volume. Now we know that for isothermal processes, the product of the pressure and the volume is just equal to a constant. Therefore, we can set P to be equal to a constant C over volume. We can simply take out C from the integral since it is just a constant anyway, thereby leaving us with this integral. By integrating 1 over V with respect to volume and applying the limits of integration, we will finally arrive at this equation for the non-flow work. Now remember that the arbitrary constant C is just equal to the product of the pressure and the volume. So we can also equate this to the product of the initial pressure and initial volume, or to the product of the final pressure and the final volume. This will leave us with this form of the equation for the non-flow work. Finally, we can use the equation of state of ideal gases to express the product of pressure and volume in terms of temperature. This will leave us with this alternative form of the equation above. For isothermal processes, the change in internal energy and the change in enthalpy are just both equal to 0, since the change in temperature in both equations is just equal to 0 anyway. Now because delta U is 0 for isothermal processes, then based on the non-flow energy equation, the heat transferred during this process will just be equal to the non-flow work. Now for the approximate change in specific entropy, remember that we can derive this by first simply taking out the temperature from the integral, since it is held constant anyway during an isothermal process. Then we remember that the heat transferred per unit mass is just equal to the non-flow work per unit mass. That is, as we all know, the integral of the absolute pressure with respect to the specific volume. We use the differential of the specific volume instead of the differential of the total volume because remember, we are trying to compute for the non-flow work per unit mass. Then, just like how we derived the formula for the non-flow work earlier, the resulting integral will be the initial pressure times the initial specific volume times the natural logarithm of the ratio of the final specific volume to the initial specific volume. Remember that from the equation of state, we can express the product of the absolute pressure and the specific volume as the product of the specific gas constant and the absolute temperature of the gas. I did not specify any subscript for the temperature anymore, since we know that it is just held constant during the isothermal process anyway. So dividing the resulting integral by the absolute temperature of the gas, we will be left with the following formula for the change in specific entropy. Remember that we can also write the ratio of the final and initial specific volumes as the ratio of the final and initial total volumes. We can further transform this equation by replacing this ratio by the ratio of the final or the ratio of the initial and final absolute pressures. Now the exact solution for the change in specific entropy is just the same as the approximate solution. The reason for this is that the final and initial S0 values, these values, are just equal since both of them are evaluated at the same temperature. So the difference of the two S0 values is just equal to 0, and we will be therefore left with this formula.